Okay. So last class we did our buffers lab. And the thing you needed to bring out of the buffers lab experience was to notice that water was really, really sensitive to the arrival of an acid or a base. As soon as you added just a little bit of one or the other, if you added a little bit of acid, the pH dropped very rapidly. If you added just a little bit of base, the pH rose very rapidly. But if you made a buffer solution, which you made using some vinegar and some sodium acetate, adding a little bit of acid or base didn't cause the pH to fluctuate wildly. Buffer solutions are something that, with so many of you going into biology, are going to be a big part of your world. Anytime you do any kind of a biological experiment, you have to buffer the system so that the pH doesn't change wildly, because biological organisms, even like us, have buffer systems internally where our internal pH is always about the same. So if you're going to do research about any kind of biology things, one of the things you have to do is create a buffered environment where the pH holds steady and equal to whatever the pH is in the system that you're trying to study. Then, as part of your post lab, you watched a little video, you got some information about buffer solutions, and essentially how buffer systems work. And the idea here is that we need to hold this hydrogen ion concentration relatively constant. That's the thing that determines what the pH of the solution is. Our buffer solution has an equilibrium set up such that it can adjust for the arrival of an acid or it can adjust for the arrival of a base, and it does so using Le Chatelier's principle. So if we took our buffer solution, and one of the things you did to it was you added more acid. So we're adding in more of these hydrogen ions. We have these acetate ions present, and the acetate ions can then grab onto the hydrogen, hold it tight, and become acetic acid, and sit over here. And with the hydrogen reattached to the acetate ion, it doesn't get measured as part of the pH. So as long as I have lots of this stuff, it can grab onto any extra hydrogens that show up, move them over to the other side, and our pH doesn't drop when we add an acid. If we add a base, the base ends up removing the hydrogen ion. Now the thing we have to remember about acids and bases is that if you have an acid and a base shows up, the two of them react to make water. And it's because acids contain hydrogen ions, bases contain hydroxide ions, hydrogen and hydroxide together makes HOH, but we tend to think of that as H2O. And that's called a neutralization reaction because we are creating the neutral entity water. But acids and bases together just get together to form water. So when we add base to our system, the hydroxide piece of the base reacts with the hydrogen ion piece of our equilibrium system, turns it into water, and now our vinegar is here to be able to replace all this hydrogen that's disappearing. So as the hydrogen disappears, our vinegar starts breaking down and turning into hydrogen ions and acetate ions, and the net result is that the pH stays relatively constant because we have something to take away any extra hydrogen that shows up, and we have something to replace any hydrogen that starts to disappear. And this will work for a while. Now, you can overwhelm the system. If you had kept adding more and more and more and more and more and more and more acid, eventually you would be able to lower the pH because you would eventually run out of these acetate ions that are grabbing the hydrogen and packing it up and moving it to the other side. So there's a limit to how long this can work, and that limit is the buffering capacity. When you're making a buffer solution, you typically know what you need that buffer solution to do, and so you would typically build it with a reasonable capacity to do what you need it to do. So today we have to get at how we're going to figure out the pH of a buffer system, short of having the red pH meter and just sort of shoving it in the solution. We actually can figure out what the pH of a buffer solution is going to be before we build it. You have this resource sheet, so why don't you pull out your resource sheet and grab a calculator while you're digging around and grabbing stuff. I always like to have you guys backing me up on the calculator work. If you need your buffer to protect you against both the addition of acids and bases, like you don't know what's coming your way, you have to protect both directions, you're going to get your best buffering capacity if you have an equal amount of the two parts. In our case, our vinegar or acetic acid and our sodium acetate. And that's going to protect you from both acids and bases. The other thing you can do to make sure that your buffering system is very strong and robust is to build your buffering system such that the pH of the buffer solution and the pKa of your acid are very, very similar to one another. Now, on the back of your resource sheet, you've got your pH formulas. You have your weak acid formulas or one singular formula that you used when you learned about weak acids and how to find the pH of a weak acid. And then this column over here has our equations that we're going to have to use with buffers. The pKa is calculated very much like calculating the pH. P means take the negative log. So the negative log of the acid equilibrium constant is going to get you your pKa. Also on the back of here, you have a table here of different weak acids and their associated Kas. You're going to get a copy of this resource sheet as the front page of your test, so you pretty much just have to know how to use the stuff that's on here. So let's start with figuring out which acid would be the best to make a buffer solution with a pH of 7. So the first thing we're going to need to do is go to our resource sheet and find all of our Ka values for these. Let's make a list of our Kas. So our first one's right here. It has a Ka of 2.9 times 10 to the negative 8th. Next one, 6.3 times 10 to the negative 5th. The third one's up near the top there, 4.6 times 10 to the negative 4th. And 6.2 times 10 to the negative 8th. Then we're going to calculate the pKa of all of these. And our best starting point on our buffer is going to be the one that has the pKa closest to the pH that we want. And remember, when we take the logarithm, however many significant figures we had in the first number, we keep that many decimal places after we take the logarithm. So armed with all of our Ka and pKa values, we have to decide which one's going to make the best buffer solution if we want to buffer at a pH of 7. This one is going to give us our best starting point. And the reason that it works out this way is that This is the formula for calculating the pH of a buffer. It's the pKa of the acid that you use to make your buffer, plus the logarithm of the ratio between the ionic compound and the acid that are being used to make the buffer. If I can make this Ka value very close, or this pKa value very close to the desired pH, then I don't have to use very much ionic compound or acid in order to adjust that pH to exactly where I want it. So if we start with this, whose pKa is already 7.21, I've only got to adjust by 0.21 pH units. If I started with this one, with a pKa of 4.20, and I've got to get that to a pH of 7, I have to make a huge adjustment to get my pH to be 7. So I'm going to pick something that has a pKa very close to where I want my pH. And then you're going to adjust this ratio to get yourself the exact pH. Now, for the purpose of this class, you don't have to be able to figure out exactly how much of these two things to use to create a buffer of a particular pH. But I like you to kind of see the big picture here of why it is that it would be good to pick something that is very close to the pH that you want to have. What you are going to have to do is be able to pick the best acid for making a buffer by looking at their pKa values, and if you're given a particular buffer solution and the information about it, to use this equation to calculate the pH of your buffer solution. Next page. Because you get these equations as part of your test, the biggest thing we have to learn is figuring out which equation to use when, and then just how to get your calculator to be cooperative and do what you think your calculator is going to do. The biggest problem people run into with these is they have a hard time deciding, do I need this weak acid formula or do I need these buffer formulas? When you're taking your test on Friday, the first thing I want you to do is I want you to look at the question and ask yourself, do I have just a weak acid, or is this weak acid creating some kind of a buffer system? If you just have the weak acid, you need this equation. If your weak acid is creating some kind of a buffer solution, you need this set of equations. Hello? Okay. Yep, that will be fine. Yep. No, that's just fine. Thank you. Yep, bye-bye. So on the back here, I've got an example of a weak acid problem and an example of a buffer problem. So this first one should be familiar from when you learned about weak acids. We need to find the pH here of a 0.125 molar solution of formic acid. So here's my concentration. As I look at this problem, there's no mention of buffering, there's no mention of a salt or an ionic compound. Okay, this is a simple weak acid problem without the complicating factor of trying to make a buffer. And I recognize the acid part of this because of the hydrogen. Having decided I have a weak acid problem, I'm going to go to my resource sheet and I'm going to pick up my weak acid formula. That's this one right here. Don't need all this fanciness because I'm not trying to make a buffer solution. So I know that my hydrogen ion concentration is equal to the square root of the Ka value times the concentration of the acid. And because it doesn't just ask for the hydrogen ion concentration, it asks for the pH. We're also going to need pH is the opposite of the logarithm of the hydrogen ion concentration. We need to go get a Ka value. Good to go. Thanks. We're going to get a Ka value here from our resource sheet, 1.8 times 10 to the negative fourth. The concentration of my acid we're going to pick up from the problem. And now we're ready to roll. My hydrogen ion concentration is equal to the square root of 1.8 times 10 to the negative fourth times 0.125. .8 times 10 to the negative fourth times 0.125 . Two significant figures, three significant figures. Round that at 2.3 times 10 to the negative fifth. And then take the square root. Square root 2.3 times 10 to the negative fifth. And because square rooting is like multiplying and dividing, the same rules that apply to multiplying and dividing are going to be involved in square rooting. 4.8 times 10 to the negative third. Or if you kept everything internal in your calculator the whole time, you'll land at 4.7 times 10 to the negative third, which is just fine. Now, don't get all excited and think you're done because we've been victorious and taken a square root, because the question doesn't ask us for hydrogen ion. The question asks us for pH, so we got to go one step further. pH is the opposite of the logarithm of 4.8 times 10 to the negative third. So the pH of this weak acid is going to be 2.32. Nothing new there. We've already worked with weak acids. But I like to have the two things sitting side by side here. Now we're going to add the buffer idea. So we've got this solution of formic acid. And now we're going to add to that some of this solid sodium formate in order to make a buffer. The way you know this is going to make a buffer is that here and here are the same negative ion. So the negative ion that was in the formic acid is also in the sodium formate. The sodium here tells you that we have a salt, which is just another name for an ionic compound. Most of your salts that you're going to use to make buffer solutions are going to be sodium salts and potassium salts. They're very soluble, they dissolve easily, so we tend to use those to be our salts. So our buffer solution here consists of the 1.25 molar solution that we had before of formic acid. And now we're taking a scoop of this sodium formate and throwing it in with the acid, just like you did when you made your buffer. You took some acetic acid out of our vinegar bottle, and then you took a scoop of sodium acetate and you put it in there as well. And you're going to take a scoop of the right size to get your formate concentration to be 0.010. So our formate is going to be 0.010. Now we've got a buffer solution. I know that I have a buffer solution because I have an acid, an ionic compound, and the negative ion in that ionic compound matches the negative ion in my weak acid. Voila. Buffer solution, different set of equations. So that's going to require this set right here. So if it was your test, best bet, just label the problem. This is a buffer solution problem. It'll help you pick the right set of equations. So the pH of a buffer solution is going to be the pKa of the weak acid plus the logarithm of the concentration of the salt over the concentration of the acid. And we need our pKa, which is the negative log of Ka. Rounding up all of our pieces. Some of them we already have rounded up. We've already looked up the Ka, 1.8 times 10 to the negative fourth. We've already dealt with the acid, and that's going to end up going there. The acid has a concentration of 0.125 molar. And our new thing is the concentration of our salt. And that's going to end up going there. Ready to roll. Okay, we need a pKa. pKa is the opposite of the logarithm of Ka. And now we can take our pKa and we can plug it into our pH equation. So the pH of our buffer is the pKa of the acid plus a little adjustment factor. Logarithm of the concentration of the salt divided by the concentration of the acid. So 3.74 plus the logarithm of two significant figures, three significant figures. We'll keep 2 on our answer here. And now we'll take the logarithm of 8 times 10 to the negative second. Negative 1.10, and our pH is then going to be 3.74 minus 1.10 our buffer solution has pH of 2.64. Okay, so those are the types of calculations you're going to have to make. With so many of you headed into the medical field, I now want to talk a little bit about the pH and the buffering of your bloodstream, because this is a really huge deal, especially if you're trying to treat somebody in kind of a trauma or a severe illness situation. The most important buffer to you is the buffer in your bloodstream. Your blood has to be buffered to maintain a pH between 7.35 and 7.45. If your blood pH gets outside that range, you start to have some ill effects on your health. So your blood does this with a buffer system that involves carbon dioxide, carbonic acid, and the hydrogen carbonate or bicarbonate ion. As you know, when you exhale, you're typically exhaling carbon dioxide that's been produced by the metabolism of your cells. But not all the carbon dioxide that's produced by the metabolism going on in your cells gets exhaled from your lungs. A lot of it gets dissolved into the water that's in your bloodstream. So your cells are undergoing metabolism. The CO2 is being produced by the metabolism, and those of you who are in AP Bio have seen all these equations for the production of CO2. That CO2 has to go into the bloodstream, which your blood is a good portion water, and that CO2 combines with the water to create an equilibrium between the carbon dioxide water and this stuff, which is the weak acid, carbonic acid. So that little equilibrium system is traveling around in your bloodstream. There's a second equilibrium system that gets set up because carbonic acid is a weak acid. So here it is down here. And we know that our weak acids establish an equilibrium between being all put together and being dissociated, meaning a hydrogen has fallen off. So this carbonic acid created by the carbon dioxide in your bloodstream has an equilibrium with these hydrogen ions and this ion right here, which is called the bicarbonate ion. And this equilibrium right here is responsible for the pH of your blood, because it's the equilibrium of the carbonic acid that creates the hydrogen ions. Now, a couple things can go wrong medically. Thing number one is that you can end up building up too much carbon dioxide. This can happen with any kind of respiratory troubles, pneumonia, emphysema, asthma, some kind of trauma to your lungs, but for some reason, your lungs aren't pulling that carbon dioxide out of the bloodstream and allowing your body to exhale it. When that's the case, we start messing with these equilibria, and Le Chatelier's principle will tell us what's going to happen. If you're not exhaling enough carbon dioxide, you have too much carbon dioxide in your bloodstream. We know that if we have too much of a reactant, the equilibrium has to shift away from there. And the net result is that we get more of this carbonic acid. But this carbonic acid is part of another equilibrium process, and because we had too much carbon dioxide, we now have too much carbonic acid, too much of a reactant, equilibrium has to shift toward products, and all of a sudden, we have more of this. The concentration of hydrogen ions goes up. That makes the pH go down. Or in other words, your blood is too acidic. This situation is called respiratory acidosis. Seems like a logical name. Literally, your blood is too acidy because your respiration isn't working the way that it needs to be working. If you encounter a patient who's suffering from respiratory acidosis, we need to reverse this entire process. We need to shove this equilibrium back to turn this stuff back into carbonic acid in order to turn the carbonic acid and shove back the other direction. So the solution to our problem is going to come in the form of an IV solution of sodium bicarbonate, which contains the bicarbonate ion, which is right there. So if I need to put the blood back to being less acidic, here comes my IV. So here's my IV solution. The IV solution serves to add product to that second equilibrium. When I add product, I can push that equilibrium back in the direction of the H2CO3. And as it shifts back that direction, because of all this extra bicarbonate, it starts to use up the hydrogen ions as the bicarbonates move to over there. So we use up the H+, and the pH rises back to normal. Now, you haven't actually solved the fundamental problem. You still don't have a way for the person to get this out of their bloodstream. You're going to have to deal with the respiratory problem. But what you've done is you've bought yourself a little bit of time to deal with the respiratory problem by at least bringing the person's blood back into an acceptable pH range. Now you've got a little bit more time to try to figure out, do I need albuterol, or any of the other things that you might be able to do for this person. Okay. We can have the opposite happen. We can end up with not enough carbon dioxide in the bloodstream. This is caused usually by somebody hyperventilating. Hyperventilation is often associated with some kind of a panic attack. Your patient is very agitated, very frightened, and understandably so. A medical emergency can be medically frightening and can send a person into a case of hyperventilation. If you've seen anybody on TV do this, you might have thought that it's very silly that the solution is to have the person breathe into a paper bag. And I can remember as a kid thinking, that is the stupidest fix for anything ever. Somebody's got to be just making this nonsense up. It turns out there is scientific validity to the idea of a hyperventilating person should breathe in and out of a paper bag. So here's what happens when you start to hyperventilate. If you breathe too rapidly, you're going to expel too much carbon dioxide from your bloodstream because you're just too much is coming out. Loss of reactant. The equilibrium shifts in the direction of the reactants. That's going to result in a loss of this carbonic acid. But that carbonic acid is participating in a second equilibrium. Okay, so this carbonic acid right here is going out to this other reaction. And as this goes out to the other reaction, now I don't have enough reactant. My equilibrium is going to shift to the left. Zoom. And as that equilibrium shifts to the left, hi, thank you. Equilibrium shifts to the left, we start to lose our hydrogen ions. And when we lose our hydrogen ions, pH goes up. That's called respiratory alkalosis. Alkaline is another word for basic. So our pH is going up, our blood is becoming too basic. So on TV, then they give the person a paper bag, like, oh, breathe into this. How could this possibly help? Well, if you have the person put a paper bag over their face, when they exhale, the carbon dioxide is trapped right here. And when they inhale again, they inhale the carbon dioxide right back into their lungs. So now they're inhaling carbon dioxide from that paper bag, because we're not letting the carbon dioxide get away. That's going to drive this equilibrium in the direction of the products. That means I'm going to get my H2CO3 back, which is going to feed into this reaction. Extra reactant shoves us toward product. Concentration of hydrogen goes back up. And the pH falls back to normal. So it turns out the advice to breathe into a paper bag when you're hyperventilating actually has some scientific validity in equilibrium. The limitation of this buffering system in your body is the concentration of hydrogen ions and bicarbonate ions can't be really, really high. Like you might think, well, gee, if the pH of my blood is so important, why is this buffering system so sensitive? We've just figured two ways that this can all basically come off the rails and your pH of your blood can get all out of whack. Well, remember from our discussion of osmolarity that our blood has to have an osmolarity of right around 0.3. That means that we can't just have more and more and more and more stuff added to our blood. There's a limit to how many things can be dissolved in our blood, because if we exceed this 0.3 osmolarity, then our blood cells start to shrivel and shrink. And that 0.3 is everything that our blood has to have dissolved in it that it needs to be moving around our body. So we have a limited capacity to carry the hydrogen ions and the bicarbonate ions in our bloodstream because we can't exceed this 0.3 osmolarity. And that kind of comes all the way back to this buffer capacity thing. There are a lot of situations where, yes, you could have a better buffer system if you could have a higher concentration of the weak acid and of the salt, but due to other constraints on the system, like your bloodstream can't exceed a concentration of 0.3 osmolarity, you can't have more and more and more of something. And therefore, our capacity to buffer our blood ends up being somewhat limited. Okay, that does it for our material that goes with Unit 4.